All right, 2019, number 4. National average 2.4 out of 4 points. We're going to fly through this one. Student doing experiments with CO2. Originally, a sample of the gas in a rigid container has this temperature. At that pressure, the student increases the temperature in the container to 425. Describe the effect of raising the temperature on the motion of CO2 particles. Here we go. Number 1, if you increase the temperature, what happens to the speed of particles? You heat them up, you speed them up. So an increasing temperature will cause the carbon dioxide molecules to move faster. That's it. Increasing temperature will cause the CO2 molecules to move faster. They put to increase the average speed of the molecules. Same difference. You get a point for that. Believe it or not, you get a point for that. That's A. Part B, the calculation part here. Calculate the pressure of carbon dioxide in the container at 425. This is crazy. This is a pressure and temperature where they change the temperature. That's it, and they ask for the new pressure. This is just a Gay-Lussac's law here of pressure 1 over temperature 1 equals pressure 2 over temperature 2. So easy that people probably missed it because it's so easy. So here we go. You get caught going PV equals nRT, right? And if you get caught going PV equals nRT, that's okay. You still get the right answer out of it as long as you keep your volume constant and your moles constant, right? If you end up with this PV equals nRT, if that's what you fall back on, then what doesn't change? R doesn't change, and moles don't change, and volume doesn't change. And what are we looking at? Pressure and temperature, right? And so pressure over temperature would equal the pressure over temperature of something else, right? You could solve them both that way. Put 1 in for the volume, put 1 in for the moles, put 1 in for R, right? And you can solve for the difference in temperature of the second one. So here we go. So pressure 1, 0.7. This is the right way to do this, 0.7 atmospheres over temperature 1. They gave them to us in Kelvin. 299 Kelvin equals pressure 2, what we're after, divided by 425 Kelvin. That's it there. Cross multiply. We should expect that if the temperature is increasing, the pressure is going to also increase. So pressure number 2 equals 0.99 atmospheres. Increase in temperature, increase in pressure. That's it on part B. Part C asks us to explain. It says, in terms of kinetic molecular theory, the movement of molecules theory, why does the pressure change in the container as it's heated to 425? The increase in temperature causes particle speed to increase, so the particles are hitting the walls of the container more often, causing an increase in pressure. Increase in temp causes particle speed to increase, so the particles are hitting the walls of the container more often, causing pressure to increase as well. That's it. Explain what's happening. It's pretty practical what's happening there. Part D, this is tough. So those are the first 3 points. Part D is a little tough because we don't do any calculations with with real gases. All of our talk is ideal gas, and when it says ideal gas here, that's the big hint in this part D. It says the student measures the actual pressure in the container at 425 and observes that it's less than the pressure predicted by the ideal gas law. Explain this. In real gases, the carbon dioxide molecules actually have some attraction for each other. Which causes, all you have to put as causes less pressure. We're talking about in real gases, those guys are attracted to each other. That's the key part of this. The attractive forces between those carbon dioxides cause a lower than predicted pressure, right? Why is that? Because those particles, as they latch onto each other and slide past each other, it slows them down when they're attracted to each other. It's the same way in the hallway, right? You guys walking down the hallway, if you're attracted to somebody in the hallway, it slows you down getting to your next class, right? It's the same thing with these molecules. It slows them down. Then they're not making contact with the walls as often. Because they're slowing down, they're not hitting the walls with the same amount of kinetic energy as they slow down. And so all those things contribute to a slightly lower pressure for that carbon dioxide. That's it on number 4.